Hello teammates, it's Mr. Nini coming to you with another Physics Bunker production. We're looking at free response question number 6. I'm pretty sure it's number 6. It's the one with the pendulum. So as we go through these, and I'll get better on opening up the solutions for you. I got a little behind, my fault. Look at those, and then I recommend you look at the videos too, because I'm going to work to provide you some tips. I think you can watch my videos with a quicker speed. So look for the tips as well. And especially if you're stuck. I think the more ways you get hit with the information, the better your brain processes it. No, I don't just think that. That's what cognitive science tells us as well. So if you only see something once, you're not going to retain much of it. And that's why many students get trapped. If they don't see the problem in the exact same way, they don't know what to do. And so my goal by doing these is to provide you some more tips on how to tackle the problem. Let's go. I thought this was kind of easy money, but it's a little deceptive if you panic. And so you're given a pendulum. We've done pendulums. You're given a position time graph, horizontal position. So read that carefully. You're given the horizontal position left and right. So, and then you're told you got a mass, you got an angle. So, and I wrote my note here, it's a small angle approximation. Recall we talked about that pendulums will be in simple harmonic motion where that restoring force is providing that force back to the equilibrium position in a periodic motion for small angles. And roughly 15 degrees is a small angle. 22.5 is what you see often in physics textbooks. 30 degrees, some instructors will approximate like that. But the key is it's a small angle. Not relevant directly to this problem, but I thought I'd point it out. And then you're going to look at, and I'm going to write this on a separate sheet of paper. It was getting crowded. So the first part, dot represents the sphere at position 2. You don't want to make any assumptions. Go back and say, okay, there's position 2. Whoops. There's position 2. And so what you know, if the pendulum bob was at rest, your forces would be balanced. But it's not at rest, it's moving, and even though the velocity is changing, so it's not technically in uniform circular motion, you've got a UCM type character to this motion, and force centripetal applies. It's the net force upwards. These are my notes. You don't have to write this on your assessment. I'm just so you know where my head is and where yours is going to be too. Force net is going to be up towards the center of rotation, axis of rotation. So force centripetal in this case is going to be your force tension plus your force gravity. That's going to give you a net force upward. So we're going to add those. And that's why I really discourage students in trying to memorize some pattern. Just say what direction is my net force and then what goes into that. And then attack from there. So your force tension must be greater than the force gravity. When you see these lines, you're probably not going to see these lines on your exam. You might. Never is a really tough word to use with the College Board AP Physics team. But you want to clearly show that the force gravity is less than the force normal. So I made it 3 blocks down, 4 blocks up. As long as you're up, you don't have to calculate a force here. So it's purely qualitative. No quantitative, not even semi-quantitative, purely qualitative, representing what is bigger than the other. Now look at B, calculate the max energy of the sphere. Well, you'd say, well, of course, we're going to find the change in Y, and we're going to apply energy conservation, and we're going to determine our initial gravitational potential energy. It's only asking us for kinetic energy, energy is conserved, and we shall know that we're done. But then you go, well, son of a gun. They didn't give me a length. And teammates, the College Board has got a whole platoon of question writers. There's probably, I've been told, about 30 of them. And so unless they make a tragic mistake, they've given you everything you need to solve the problem. It's not like they left it out. So you're going to back up. You're going to say, okay, what can I do? And you'll notice what you've been given. The horizontal position is irrelevant. But we got the period here, don't we? And so you think period, pendulum, period, pendulum, hot diggity dog. You're going to say, I'm just going to, so I don't distract you here, go piece by piece. You're going to say, I can get the length of the pendulum from my pendulum equation. And so you're given you gotta discern the period. The period's 2 seconds. Peak to peak, trough to trough, 2 seconds. You got a period of 2 seconds. You're gonna set up teammates that want you to do this. You're gonna set up your equation. Period of pendulum, 2 pi over length, square root of length over g. And they want to see you go step by step by step. They don't, you will not, next Thursday, no, Thursday after next, you will not, if you're prudent, go from this to your answer. You want to go step by step. Break it down. So you're going to divide both sides by 2 pi. You're going to square both sides. And you're going to identify, therefore, L is G times period over 2 pi squared. This next step you don't really have to do. I kind of, what do you call it? Exploded it so you can see the detail, right? If you ever look at a diagram, how a machine is put together, sometimes you'll see a diagram and the parts are all pulled apart. That's what I did here. And I want to make a couple points. I want to reintroduce this concept. You may see this on the exam. 2 newtons per kilogram. You go, what the heck is that? It's acceleration, right? 10 meters second is the same thing as 10 newtons over a kilogram, because a newton is a kilogram meter second, mass times acceleration, force, mass times acceleration. Newton, kilogram meter second, divided by kilogram gives you meter second. Now, why do they do it like that? I don't know. But they do it. They do it. And so now you're prepared. You're going to solve. And here, you're going to remember this too, right? You're going to square the 2. And when you square 2 pi, you square the 2 and the pi. You're not going to go 2 pi squared. You're going to square the 2 and square the pi. It's good. You get 1.01 meters. You can 2 decimal places is fine. 1 is fine for some problem like this. If you get a 0.01, you can ignore it. All that was 1 point. And the next part, you got to walk it through. You got to walk it through the next. So first, Mr. Reader man or woman, I determined the period. The length, I'm sorry. Now I determine the change in y. Recall that change in y is length minus L cosine theta. And that's because if you displace it by some angle theta, your length, you take the cosine of that length, you're going to get this side, there's your right triangle. L minus L cosine theta is going to give you a change in y. That's how that comes about. It's going to be small for a pendulum. It's going to be small. Now we got our change in y. We can see the goal. That's 1 point. You're going to apply the energy conservation equation. You're going to specifically articulate this is an energy conservation problem. If I determine the gravitational potential energy, I know the kinetic energy. You're going to be explicit. UG equals KE. UG equals mg change in y. You're going to put in your values. You're going to solve, and you're going to write your solution. You're going to circle it. Oh, you're going to if you write it on a tablet or something, if you type it, I don't know that you want to. I don't know. We're just, if you're going to type, just type. I don't know why I wouldn't get too fancy on that. It's good. 3 points. Last one. New angle is less. How does your motion change? So you 2 points. I think it's 2. I'll have to look. I think it's 2 points. So you're gonna say you can't just say, teammates. If you just say it doesn't change, you get no points. Even though you're right, you will get 0 points for that. You want to say why it doesn't change, Mr. Reader person. It doesn't change because in my period for a pendulum equation, the displacement doesn't matter at all. And so because the displacement doesn't matter in terms of the period is not affected by displacement. And I just put in as long as small angle. You'll make the grader very happy if you write that, if you get a problem like this. I don't know that they're going to be excited about that. But what's going to change, smaller angle, smaller change in y by, and again, even though you wrote it up here, you're going to say it again. Change in y equals L minus L cosine theta. Smaller angle, smaller KE by, and you're going to walk them back through that. And you are going to do your happy Snoopy dance and get max points. It's good. Hot dog, teammates. I thought this was a really good problem. It was kind of deceptive. I bet some of our teammates looked at that pendulum and said, we've done pendulums. Why am I going to? Then you saw that, and now you know. Have a great day, teammates.